我
You will online.
你
I
说
will
你
in
在
person and another people will online.
哦，yeah yeah 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 yeah.
Yeah.
Got it got it got it. So you're the president, right?
Yeah, I'm also present.
Okay. So where the Shane where the
It's not. Yeah.
oh he will not come here for the whole conference, right?
Yeah. Maybe it can. You come here this month.
Oh, okay,
Yeah.
okay, got it, because he has session is.
Oh, yeah, yeah. Well,
my
good.
session,
Yeah, that's it.
usually we need his support.
Yeah, no worries. He will.
Oh, he will come.
Yeah,
no
he will come. Yeah,
no problem.
Yeah.
Okay, enjoy your talk.
Thank you.
哦，你的也没有那个。
哎，你能放我们进来吗？等等，我我现在放我进来。
视频。他把那个 webcam 拿走了。啊，还没开始。什么？他这个没有那个线，都不
哦，
行。
没事，这个倒不重要。嗯，
我看着他把 webcam 拿走了，他说要录制。我们现在有声音。
没事，
把音
你
频关了。
不要有共享，我那我
你再试一下，是不是？喂喂喂，好像是在我这里发出来的。喂，你说一句话。嗯，呃，你是不是静音了？我把你换成主持人了。我说我把你电脑换成主持人了，我不知道是不是。
算了，没事，开始。
The
will
voice
receive
came
audio.
from me.
Yeah. So let's check now.
Mhm.
Okay. So are you on the call now?
What? Sorry?
Is the call on now? Are you on?
Yeah, it's on now.
Okay. So would you like to speak?
Hello. Oh, that's correct.
Just a second. It's too much. I have feedback. Okay. So
What if
that's
I
good
want
with the.
to record a video?
You shouldn't be the
Absolutely.
guest.
Hello? Okay, I think it's
It's
correct.
working.
Yeah, okay,
Okay, we need to make sure your laptop is muted.
yeah.
We don't have the camera on. Check, 1, 2, okay. Check, check, 1, 2. No, this is not muted. We need to mute this, the audio of this. Yeah, so we go to audio, mute this first.
Oh, I have. Yes.
Not here, from the laptop, not from Zoom.
Is that okay?
Not from the laptop, from Zoom.
Oh, I have from laptop.
This
Yes.
is Zoom.
Yeah.
So we need to activate this and this.
Okay, activate this. Okay.
Okay, let's mute from the laptop. The audio, somewhere here, where's the audio?
Okay. So next.
So Zoom is muted. Okay, okay. So I can see you, which is very good.
Yeah.
But you need to see me. You see me here.
Yeah.
Can we send this here? Oh, because it's on mode, presentation mode, you cannot.
Yeah.
You should be able.
Yeah.
If we share the Zoom page,
So it means I have
is this the Zoom page or this is the PowerPoint?
the PowerPoint.
Can we put the Zoom page, the Zoom screen?
Oh, yeah, I can get the Zoom.
Did you get what I mean?
Yeah.
Yeah, that's it. This is what we want. So if you could put this in the corner somewhere, it doesn't affect your presentation. And we don't need video from you. You are just recording. Yeah, that's it. Perfect. We can see the host. We can hear him. I had to mute it. Check. We need to check there. No, that's why I told you, you shouldn't mute Zoom. You should mute the laptop because you can't hear me, I think.
Yeah.
Have you plugged the audio? Yeah, that's it. Did you get what I mean? Okay. So you mute your laptop, not the Zoom. You go to laptop and mute the speaker. Okay, that's perfect. Because if you mute the audio, you won't hear me. So is this recording?
Yeah, it's
You can see both and you have the presentation. It's recording, right?
yeah.
Perfect. I think we have done what we need. That's it. Everything is working. Okay, just let me check this mic if they, in case they have like a question, make sure this is working. Check. Testing. No, you are still muted. So you are muting the Zoom. We need to mute the laptop, not Zoom. Check. Check. Now I can hear. If you mute Zoom, I won't, as a host, I won't be able to hear anything
Okay.
because this is recording and going as feedback.
Yeah.
But now, in this case, if you don't mute Zoom, I will be able to hear you and hear the guests here. Check. Check. It's working. Okay.
Okay.
All right. So we are done. You can turn off everything because you will be here. I will show you just simple things here. Yeah. So the first two, this is the mute button for each mic we have got here. We have got the first two is the mics, the lectern, two mics. The third one is this one. This can be here on the charger all the time. I will have it here on. Take this one out. It's gonna be green. Check it's working. If it's red, check it's not working. So you need to press one press, not hold, just press. One press, it's green, okay? And when you put it there, just make sure it's red. So when you put it, doesn't make noise. The third one is the electrical feedback, is what we hear from the host. And the last one is the playback. It's what we hear from the recording coming back. That's all. Just make sure they are all on. And you don't need to be the level. It's okay. I will be outside. If you struggle anything, just go and I will come outside. Okay? That's it. Okay. I think everything is sorted. Leave.
Yeah, thank you. Okay. Where's my phone?你的手机吗？哦，来，我们可以开始。行，你帮我 record，不在我这里。没事，你先帮我 record，然后就可以。
需要录视频。他说
那边 record 就可以了，Zoom record 就可以了。
已经在 record。
OK。
那我要另在还是直接开始？还是说
退出重新开始一下吧。Okay, let's begin. Sorry for late. Hello everyone, my name is Xing Shen, and I'm a PhD student at the University of Queensland. I'm supervised by Dr. Xin Yu and Professor Zi Huang. Today, I'm very honored to present our workshop about sign language. The first part is about the isolated sign language recognition challenge, designer, results, and future research. Our workshop is organized also by He Mingzhu, Xu Miao, and Xin Yu from the University of Queensland, and Miao Miao from the Australian National University. In this workshop, it will include the following content. First, I will introduce the background and motivation of the sign language. Then I will talk about the Word Level Auslan dataset, which is a dataset we used in this challenge. After that, I will explain how we designed the challenge. Next, I will show the results of the challenge and we invited participants to share their method. Finally, I will discuss some ideas for future research. Here I present some data related to deaf individuals. Hearing loss is becoming a bigger issue, both worldwide and in Australia. Firstly, globally, the World Health Organization reports that over 5% of the world's population suffer hard of hearing. By 2050, this number is expected to rise in 700 million, or 1 in 10 people. In Australia, as of the 2050, 1 in 6 Australians suffers from hearing loss. By 2015, this will increase into 1 in 4. Sign language is a primary mode of communication for many deaf or hard of hearing individuals. Each sign language processes its own vocabulary and grammar rules, like the spoken language. Notably, even writing region shares a commonly spoken language, such as the United States, Australia, and the United Kingdom. Sign language are different. Following on the background data, deaf and hard of hearing individuals will become a large group and face significant challenges in the daily life. For children, they may drop out of school, and for adults, the impact can be in the workspace, with some facing job losing. Additionally, many experience social isolated because sign language is often their primary way of communicating, making interactions with another more difficult. To address this issue, two strategies can be implemented: enhance the level of the medical care available, or use modern technology to help individuals with hearing loss integrate into daily life. Recent advances in technology offer new hope. With the growth of the deep learning technology and the availability of the large-scale sign language datasets, sign language processing achieves promising progress. Isolated sign language recognition is a fundamental task in the field of the sign language understanding. Isolated sign language recognition focuses on identifying individual sign language signs. The input is a short video with only one sign, and output is corresponding gloss annotation. This input is a short video with only one sign, and output is the annotation gloss. Gloss is a unique label for a single sign. Each gloss is identified by a word of race, which is associated with a sign's semantic meaning. Considering the diversity of sign language across different regions, developing region-specific isolated sign language recognition dataset is important for supporting communication and research. Auslan, as a sign language specific to Australia, still lacks a large-scale world-level dataset for isolated sign language recognition task. Moreover, most public available datasets have limits in gloss dictionary size, depth information, and recording perspectives. To fill this gap, we create the first large-scale multi-view, multimode world-level Australia sign language recognition dataset named World-Level Auslan. Compared to another available dataset, our dataset accepts three significant advantages. The first one is the largest amount of data, the most extensive vocabulary, and the third is the most diverse of multi-mode camera view. And in this section, I will introduce our proposed world-level data Auslan data set. This figure shows that recording environment we used. We set up 3 Kinect V2 cameras and 1 real sense camera around the signer. We set up 3 Kinect, the cameras are placed at the different angles to capture the signer's movements from the multiple views. We also used a green screen background to make it easier to progress in the video later. Here are some sample images from our dataset. We captured multi-view and multi-mode data. As you can see, our signers shows great diversity in both age and race. For each data samples, we provide multiple types of information, including RGB videos, depth snaps, and key points. This different modality help capture both appearance and the movement of the signer in detail. Now, I will show some statistics about our data set. We analyze the diversity of signer, the complexity of the gloss, and the coverage of the vocabulary. The first pie chart shows that the distribution of the race and gender among the signers. And the middle bar chart shows that the frequency of the polymorphous gloss. It means that for each gloss, it may have the multiple meanings in spoken language. And in the third pie chart, we also show that we investigate the signers with a different Auslan background, including Auslan experts, deaf individuals, and learners. Finally, our data set covers a wide range of the word categories. In our data set, we select 3,215 commonly used Auslan gloss, corresponding over 7,900 English words of or phrase. And after 2,015 hours of recording, we captured more than 200,000 videos by 73 signers. Compared to all existing isolated sign recognition data sets, our data set is largest and including both multi-views and depth information. To evaluate the performance of our isolated sign recognition systems under real-world scenario, we provide a diverse test set with 4 distinct subsets, including studio sets. It's same with the training data. And in the wild sets, we capture in the studio without green background. We extract signers from the videos and the semantics indoor and outdoor background in the semantic set. And for the last TED set, we simulated the potential recording time mistakes in the real-world scenario by randomly adjusting video segments through remove or alternating playback speed. We split the samples of a gloss into the training, validation, and test sets following a ratio of the 6:1:4. Additionally, we further divided the test set into 4 different test sets into the same ratio. To make our benchmark more comprehensive, we train and test all the state-of-art model in different isolated sign recognition settings. First one is the most common setting. It is a single view RGB-based isolated sign recognition. It involves recognizing isolated sign language from the video sequence captured from a single fixed camera. This is a experiment result. It can be observed that RGB-based model perform better than the post-based model when the background remain constant. However, when the background changes, post-based model outperforms the RGB-based model as they are unaffected by the background variance. Additionally, the best performance is achieved when the multiple multimodalities as the input. And the single view RGBD-based isolated sign recognition aims to enhance the recognition of the isolated signs by incorporating depth information along with RGB data. From this table, we can see that the addition of the depth information improving the performance of all models compared with the RGB-based isolated sign language recognition. We also provide the experimental results for multi-view RGB and RGBD ISR settings. Since our data set was recorded with 2 different types of RGBD cameras, we also introduced a cross-camera ISR setting. The performance in the cross-camera settings is dropped, showing a significant gaps between the cameras. This highlights the cross-camera ISR remain a challenge task. And we also conduct the cross-view test. We train on one wheel and test to another two wheels. The result I'm showing here, it indicates that this is a highly challenging task. It is also a real-world issues that is was for future research. And in summary, we construct the first world-level Australia isolated signage recognition dataset. It captured by the multi-view RGBD cameras and enabled to investigating of various of multi-mode ISL sightings. And for each ISL sightings, we establish a leaderboard and evaluation benchmark to promote future Australia Sign Language recognition research. As we showed in the benchmark result of the multi-MM world level Australian data set, our models performed poorly in cross-view testing. This is findings motivate us to design a specific challenge for each difficult cross-view isolated sign language recognition task. And next, I will introduce the design of the challenge. Now, let me introduce the designing of the cross-view ISLR challenge. The goal of this challenge is to test how wheel model can recognize signs from different viewpoints. And we have two tracks. The first one is RGB-based ISLR, where the model trains on the frontal RGB videos and tests side view. And the second is RGBD-based ISLR, where the model uses the RGB and depth data to improve generalization. We use the MMO level Australian data set, which provides a multi-view and multimode sign videos. The records were made with 3 Kinect feature cameras arranged in the half circle around the signer. To make the test more realistic, we use our mentioned before the diverse test set. Finally, we use a model using top 1 accuracy. Next, I will summarize the challenge results. The challenge started at November 5th in the last year and end of the last year. We have the 33 teams competing in the RGB track and 11 teams in the RGBD track. In total, we received more than 120 submissions during the challenge. Now let's look at the leaderboard. The VIPL SLP achieved the first place in both RGB and RGBD tracks. TON and JK ranks second and third in the RGB track, and in the RGBD track, Wang and the JK took second and third place. Overall, the top teams show the strong performance compared to the baseline. Next, we will investigate the teams to share their solutions and ideas. And the first one is, let's welcome to the team, Wang's team to present their approach about exploiting example learning for cross-view isolated sign language recognition. I think I will stop sharing. Hello,
Hello. Well, wait for a minute.
can you share your screen? And I
Uh,
can,
okay. Thank you. Wait for a moment.
yeah.
Our team member Zhang Lingduan cannot share his screen. Maybe you need to invite he
Okay.
to
As
panelist.
does he in the Zoom now?
Yeah, but he is in attendance.
Yeah. You can double check he is already in the as a guest.
Okay.
Hello.
Yeah, we can hear
Okay.
you.
Wait for me a minute. Now I will begin my share.
Okay.
Can you hear me?
Yeah, we can hear you.
Okay. Good morning, everyone. Thank you for taking the time to watch my presentation. My name is Zhang Lingduan, and today I'm honored to present the work of our team titled Exploiting Ensemble Learning for Cross-View Isolated Sign Language Recognition. I hope my presentation will be helpful to you, and I sincerely appreciate your interest in our work. We propose a solution for the CVRSLR challenge and WWW 2025, addressing the challenges of recognizing sign language from varying viewpoints. Traditional ISLR datasets mainly focus on frontal views, while real-world scenarios involve significant variations in camera angles. To tackle this, we adopt an ensemble learning strategy based on a multi-dimensional video swing transformer model, which enhances the robustness and generalization ability of our approach. Our method got top 3 rankings in both RGB-based and RGBD-based RSLR tracks, demonstrating strong effectiveness in handling the challenge of cross-view sign language recognition. The introduction to our work will be divided into 4 parts: introduction, method, experiments, and conclusions. CVRSLR aims to address the critical challenge of recognizing sign language gestures from varying camera angles. While traditional isolated sign language recognition datasets typically capture videos from a fixed frontal view, real-world scenarios often involve significant variations in camera positions. As a result, model must be capable of interpreting gestures from multiple viewpoints, making cross-view recognition a key problem in advancing practical sign language understanding. The MMWL Auslan datasite is the first large-scale, multi-view, multimodal, world-level Australian sign language recognition dataset, specially designed to tackle the challenges of CVISLR. It comprises over 28200 sign videos covering 3215 commonly used Auslan glosses performed by 73 sign singers in a studio environment. The data was captured simultaneously using 3 Canonical V2 cameras and 1 RealSense camera. Hemispherically, arranged around the scenery to simulate real-world scenarios with diverse viewpoints. To ensure comprehensive evaluation, the dataset includes 4 test subsets that address dynamic environments, background variations, and temporal inconsistencies, providing a strong foundation for developing robust recognition model across multiple view and modalities. CVR-SLR presents 2 main challenges: viewpoint variability and gesture complexity. Viewpoint variability arises from the need to recognize gesture captured from diverse camera angles. Gesture complexity stems from the intricate and subtle movements of hand gestures, which can vary significantly even for the same expression. The following figure illustrates the MMWL Auslan dataset designed for CVR-SLR, which provides a comprehensive collection of RGB and depth video recordings. Both the training and validation sites consist of video captured front view, supporting model learning and selection. The test site includes videos recorded from the left and right views, enabling a thorough evaluation of model robustness across multiple view angles. This structured design ensures the model are trained and assessed under realistic cross-view scenario, prompting better adaptability in real-world applications. In our work, we propose integrating ensemble learning into CVR-SLR framework to enhance robustness and generation. By doing so, the model can better handle the variability caused by different camera viewpoints, which is crucial for improving real-world performance. Additionally, we explore the use of multi-dimensional video swing transformer blocks. By incorporating different model sizes for both RGB and depth videos, we are able to capture a variety of features and different granularity, which further enhances the recognition accuracy. Finally, we integrate the result from both the RGB and depth streams through an ensemble learning. By leveraging complementary information from both modalities, we ensure optimal performance and achieve more accurate cross-view sign language recognition. In step 1, we utilize the multi-dimensional video swing transformer blocks with varying model size for both RGB and depth inputs, aiming to capture features and different granularity and boost recognition accuracy. Here, I would like to introduce the design and advantages of our multi-dimensional VST approach. The VST models both global temporal dependencies and local spatial features through a hierarchical spatial temporal framework. Its architecture is composed of 4 stages, each incorporating 3D shifted window-based multi-head self-attention mechanism to enable efficient and localized feature extraction. Within each VST block, operations alternate between regular and shift 3D window partitioning, allowing the model to capture both intra-window and inter-window dependencies. This design is achieved through two key modules: 3D window-based multi-head self-attention and 3D shift window-head multi-head self-attention. The hierarchical structure progressively downsample feature through patch merging layers, concatenating neighboring tokens and projecting them into a lower dimensional space. This enables the model to effectively capture fine-grained spatial details and high-level temporal patterns, which are critical for accurate sign language recognition. To better address the challenges posed by CVRSLR, we implement multi-dimensional VST blocks with three model sizes: large, base, and small, applied to both RGB and depth inputs. By leveraging the different model skills, we are able to extract features at varying levels of granularity, significantly improving recognition performance across diverse viewpoints. In step 2, we integrate ensemble learning to improve robustness and generalization, enabling the model to handle viewpoints variability effectively. Ensemble learning improves performance and robustness by combining multiple models, effectively reduce bias and variance, and significantly enhance accuracy, especially in complex tasks with high variability. In step 3, we combine the outputs from RGB and depth streams through ensemble learning, leveraging complementary information for more accurate cross-view sign language recognition. Specifically, we design a two-stage ensemble learning approach tailored for CVRSLR. First, in the single model classification ensemble, for each modality, RGB and depth, we integrate the outputs from the large base and small VST models. By combining different model sizes within the same modality, we achieve a more robust classification result. For the RGB-based ISLR task, the output from the RGB branch is used directly. Second, in the multi-model fusion classification ensemble, after performing single modality integration, we further conduct cross-model fusion. We integrate the feature from the both RGB and depth models to boost recognition performance for the RGBD-based ISLR task. This two-stage ensemble learning strategy effectively leverages the strengths of both multi-dimensional VST models and cross-model informations, enabling strong generalization across different views and modalities. We use the MMWL Auslan dataset, and the evaluation metric is top 1 accuracy. As shown in the figure, our model achieved the top 3 rankings on both the RGB and RGBD tracks. In this figure, it demonstrates the improvements brought by ensemble learning across different tests. Finally, let me summarize the primary contributions of our work. First, we propose integrating ensemble learning into CV-ISLR framework to enhance robustness and generalization. This approach allows the model to better handle viewpoint variability, which is critical in cross-view sign language recognition tests. Second, we investigated the use of multidimensional video swing transformer blocks. By incorporating different model sizes for both RGB and depth videos, we are able to capture a variety of features and different granularities, leading to improved recognition accuracy. Third, we integrate the result from both the RGB and depth streams through ensemble learning. By leveraging complementary information and both modalities, we ensure optimal performance and achieve more accurate cross-view sign language recognition. That's all for my presentation. Thank you for your attention. If you have any question about our work exploiting ensemble learning for cross-view isolated sign language recognition, you are welcome to download the original manuscript for more details. Additionally, feel free to contact us via email for further discussion. Okay, that's all.
Okay, thank you, Li Kun and Kun Wang, for your great good presentation. And I will go back for our PowerPoint here. Yeah. Go back to our PowerPoint. Okay. Thanks, Wang and Kun again for their presentation. Okay, I think someone do not mute yourself. Okay. Okay. And the vaccine explores an Okay. The vaccine explores an example learning approach based on the video swing transformer to enhance cross-view ISL. Their method integrates multiple VST models of different sizes, such as large space small, to extract spatial and temporal features from RGB and depth inputs. A two-stage ensemble strategies is used first. Firstly, single model ensemble, and then within the RGB and the depth modality, then a multi-mode ensemble combinations, both branch to improve the generalization. And the next, let's welcome to the teams, Xinyu Wang's teams to present their approach about cross-view isolated sign language recognition with a graph. And, 英语, can you hear me?
Yeah, I can.
Yes.
Um,
So share your screen.
sorry, but I don't have the button which could make
Oh,
me
wait a
share
minute.
my
I will
screen. Okay.
Maybe I can give you save you as a gesture. You can allow that and share your screen. Yeah, okay. Thank you.
Wait. Hello, everyone. My name is Wang Xinyu, and my research topic is cross-view isolated sign language recognition with graph. And I feel very honored to share my work with you. I'd like to talk about my research from 4 sections: introducing the background and the objective for the cross-view isolated sign language recognition task, the literature review, the methods, and the results of my work. The first section is introduction. Sign language has a significant impact on the people with hearing impairments as the primary means of communication for them. Due to this, ISLR is highlighted as a fundamental sign language learning task, which aims to recognize individual sign glosses from sign language videos and translate them into commonly used words or phrases in spoken language. However, current ISLR research mainly concentrates on videos only from the frontal perspective, which does not align with real-world application scenarios. In practical situations, the camera capturing the signers may not necessarily be positioned directly in front of them. Therefore, word level of slang has been introduced to address this issue. Based on this dataset, we propose a novel graph-based approach for isolated sign language recognition, which captures spatial and temporal relationships within and across RGBD video frames. This effectively integrates multimodal data to improve recognition accuracy. The last section is the literature review. The goal of the isolated sign language recognition task is to predict the corresponding gloss from the video. ISLR achieved significant progress and obtained high recognition accuracy in recent years due to the development of deep learning architectures and the surge of computational power. 3D convolutionary neural networks emerge from extracting spatial temporal features, and many sign language recognition methods are developed based on them. Meanwhile, RNN that enables modeling sequence information also draws extensive attention in sign language recognition. Due to the successful application of transform in computer vision tasks, there are more researches focusing on transformer-based structure to improve the recognition performance. Besides, recent studies also show that combine multiple modalities significantly improve ISLR accuracy. Some of them use a simple example method to example all the modalities with assign weight to the every modality according to their accuracy on validation sets. Sum these predictions up with weights as the final predicted score. And now I will introduce the method. In this section, we present the details of my method. It consists of 4 major components: image subdivision, the graph network within a single frame, the graph network across the entire video, and the division of RGB and depth. And the overall structure of the model is shown in this figure. At first, we use a patch file system to convert each frame into N patches and obtain the corresponding visual feature values for each patch, which we treat as a node in the graph. In the previous stage, we perform initial processing on the video by subdividing each frame into N patches, treating these patches as nodes in the graph. To incorporate information from each region in the frame, we also need to connect the nodes with edges. However, if we connect every pair of nodes with edges and use this as input to a graph neural network, the computational complexity would increase. In addition, redundancy in the information might negatively impact the recognition performance. Therefore, to reduce complexity, we employed the k-nearest neighbor algorithms to select k-associated nodes for each node depending on the similarity. And to measure similarity between two nodes, we choose the Euclidean distance function. By processing each node in this way, we obtain a graph that contains the nodes and edges. At this point, we can use graph neural network to process the resulting graph. In style language recognition tasks, in addition to establishing the relationships between different regions within the same frame, the most important aspect is motion of the fingers, arms, and the signer's body between frames, which largely determines the growth corresponding to the sign. Therefore, we need to pay close attention to the signer's movements. After modeling and processing each individual frame with graph network, we further process the multi-frame video across the time series. Similar to the previous section, if we want to establish an edge between every pair of nodes, between two frames, the information that our network needs to process would become complex and redundant. In fact, what we care about between different frames are the positional changes of the same body parts, such as the relationship between the same hands in different frames. Thus, we also choose the Euclidean distance function to describe the relationships between different nodes in adjacent frames, and we discard some of the points based on this. For two frames, we could obtain two nodes. These nodes are passed through another non-ball weighted linear layer, and their features are mapped into the distance space. We then compute the Euclidean distance and select the k-most similar node pairs, keeping the corresponding edges. Finally, we input these nodes and the returned k-node pairs as a final graph into the graph network for further processing. After processing RGB and depth information through the 3 steps mentioned above, the future of each modality is extracted with the future module. We save the output of the last fully connected layers of each modality before submax layers. We assign weights to every modality according to their accuracy on validation state, and then we sum them up with weights as our final predicted score. Finally, the table presents the evolution study of cross-view isolated sign language recognition on the word level Auslan dataset, which consists of 4 subtest sets: STU, studio in the wild, synthetic background, and temporal disturbance. Our method achieves an average top-line accuracy of 33.97%, significantly outperforming the baseline model. This demonstrates the effectiveness of our approach in leveraging both spatial and temporal relationships within RGBD data. By combining RGB and depth modalities, our methods achieve the best performance across all subtest sets, further demonstrating the complementary nature of these stage types. The highest accuracy is observed in the STU stage, where conditions are controlled while accuracy declined in ITW due to the challenges of uncontrolled environments, in SYN due to background noise, and in TED due to temporal disturbances. These results highlight the robustness of our method in adapting to diverse real-world challenges, demonstrating its generalizability for cross-field isolated tasks. That concludes my presentation. I appreciate your attention and thank you for all your time.
Okay. Thank you, Xinyu. Thank you for your presentation. Yeah. Xinhua's teams progress a graph-based approach for cross-view ISLR, leveraging spatial and temporal relationships in RGB videos. Their method model video features as a graph where needs the representation patch of the frame, and the edge capture the inter-frame and the inner frame dependency. A graph convolutional network progress these relationships to enhance the recognition. They reduce computational cost. They applying a selective edge construct strategy, discovering in relation connects. They are further combination RGB and depth modality using an example method, weighting each modality based on validation accuracy. And let's use my screen in the Zoom. Okay, I will. Where is the Zoom? I cannot find it. Slides. Yeah. No, not slides. I think the Zoom. I need to reshare my screen. Okay. Sorry. I will restart. Okay. Okay, let's continue. Since Zheng Zhongtian is not available to present today, I will give a benefit summary of their work, titled is a zero-shot multi-view Australian Sign Language Recognition. Zhongtian's method applies a view conditional diffusion model to enhance cross-view ISLR. This syntax the multiple side view pose estimate using a large-scale diffusion models, improving their training data diversity. Their framework is integrate RGB features to complement the skeleton-based method in enriching context understanding. Additionally, they implement the movement-guided temporal segmentation to remove the non-informative frame and employing a special temporal GCN and TCN for dynamic feature extraction. A multi-mode example strategy is further refine the predictions. And for more detail, you can read their paper and ask their questions. And this is for the first part of our workshop. And if we do not have any questions, and we can go into the morning tea times. And the next workshop will begin into the 11 o'clock. Okay, let's continue to our workshop. And after the first part, we have been the three talkers give our talk about their method to solve the isolated silent recognition methods. And finally, we have the last one from the Yue Congming and Yuting to give their presentation about the approach of authentic real measurement for silent recognition. And I will. Yeah. Yuting, can you hear me?
Yeah, I can.
Yeah.
So I'm gonna share the screen.
Yeah, can you?
Okay,
Thank you.
thank you very much. Okay, so I'll start the presenting. And hello everyone, I'm Yuting Peng from University of Chinese Academy of Sciences and the Institute of Computing Technology. Can you see my screen correctly?
Yeah, it's correct.
Yeah, thank you. So today I'll present our paper titled Synthetic View Augmentation for Sign Language Recognition. It's a joint work with Pei Qijiao, Honggang Zhou, Yue Congming, and my supervisor, Xilin Chen. It's our great honor to attend the Crossview Isolated Sign Language Recognition Challenge. Sign language recognition is a technique that recognizes the meaning of the sign language videos. Most public datasets used to train SLR models are recorded from front views, where the camera is positioned directly in front of the signer. However, these limitations are hard to follow under real-world scenarios. Consider the environment where people are conversing using sign language. For example, daily conversations and some deaf theaters. Under these circumstances, we cannot always guarantee the front views when recording sign videos. These non-front views introduce additional complexity for sign language recognition, leading to the cross-view SLR challenge, where models are required to generalize across varying viewpoints. To simulate real-life scenarios where models are trained on the front view but deployed on different views, cross-view SLR setting restricts the training and validation data to front view and testing data to side view. Under the strict setting, four main challenges are reviewed. First, models are required to recognize gestures on the views it hasn't seen during training. Second, side views often cause gesture occlusion. The bottom left videos are taken from different views with the same gesture. As you can see, while the hand is clear on the front view, it is partially occluded on the left front view. Third, the directions on the side views are ambiguous. The bottom right videos correspond to two labels on the front and left front views, respectively. The first one shows simple front-back motion, while the second one shows left-right movement as well. Although the difference is clear on the front view, these two gestures seem to be identical on the side view because the left-right movement becomes nearly invisible. Fourth, inaccurate depth estimation hinders the model's ability to accurately recognize object positions. Before presenting our method, we contextualize our work within existing cross-view research. MMW Auslan is a large-scale Australia sign language dataset for isolated sign language recognition tasks containing multi-view, multimodal sign videos with diverse backgrounds. For the cross-view setting, the training and validation sets remain consistent with the studio setting under the front view. The test set contains left front and right front views categorized into 4 subsets. Evaluation conducted on the MMW Auslan dataset in the cross-view SLR setting reveals significant performance degradation, highlighting the challenges model face in generalizing to unseen.
Loud, you put this down.
Sorry, what did you just say?
The microphone's away.
Is there something wrong with the screen or the audio?
Ask if they can get closer to the mic.
Can you get
ask
closer
if
to the
if
mic?
she can get closer to the mic? Is this muted?
So the voice is quite vague, right?
Yeah, that's right.
It shouldn't be
Okay.
affected. Your
I'll
mic should be
consider-
connected to this,
Maybe because
to the USB. Let's go to the mic and send your mic. It's getting from here. So your mic, let's go to settings. Or
Is
your
it clear
settings.
now? Is it clear now?
Let's go to your settings.
Hi, hello, is it here? Can you hear me now?
Yeah.
Get the audio from this Blackmagic, not the speaker.
Okay, so I'll continue presenting.
I think you continue, please. Thank you. Sorry about that.
Okay, thank you. Thank you so much. Okay, so the evaluation highlights the challenges models face in generalizing to unseen views. In the field of cross-view action recognition, some methods utilize multi-view or synthetic data sets to learn view invariant features. However, collecting such data is costly. To tackle this problem, Vero et al. Employed a monocular 3D human body reconstruction technique to generate scalable synthetic videos, showing its effectiveness in various settings. To tackle the cross-view SLR challenge, I propose the XV SLR model. First, to simulate the variations in both viewpoints and backgrounds, we employ a synthetic view augmentation method to generate cross-view training data, enabling the model to learn view invariant features. Second, to enhance the representation learning process, we adopt a two-stage training approach. We first train modality-specific models to extract features for each modality, then fuse features from different modalities to leverage complementary information. Our complete framework is shown above. I will begin with the synthetic view augmentation process and proceed to the final multi-model fusion in the following slides. In the synthetic view augmentation process, we first estimate human mesh from RGB videos, then augment the viewpoints, and finally integrate different backgrounds to generate various input data. The human mesh estimation is completed using an off-the-shelf human mesh recovery model, OSX. We first estimate human parameters using OSX, then feed these parameters into simplex layers to get 3D vertices and joints. The vertices are further used to render human mesh, and the joints are directly used as 3D skeleton key points. Then we apply viewpoint augmentation to the estimated human model. We only do view augmentation for depth and skeleton modality due to the high rendering cost for RGB data. Specifically, we first rotate the 3D human mesh, then project the 3D human mesh onto the image coordinate system. We set the rotation along the x-axis to range from -10 to 10 degrees, and the y-axis rotation from -30 to 30 degrees. To further adapt the model to different backgrounds, we also integrate various background to RGB and depth data. After generating synthetic data, we feed the augmented data into a multi-model fusion module to leverage complementary information from multiple modalities. First, we extract single model features using modality-specific models and supervise the training with cross-entropy loss. For RGB and depth data, we leverage a large-scale pre-trained model to initialize feature extractor. For skeleton data, where no comparable large-scale pre-trained model is available, we adopt a modified version of previous work cosine and further stock a bidirectional LSTM to capture full sequence temporal dependencies. After extracting features from 3 modalities, we concatenate them and prepend the learnable embedding, then feed the sequence into a fusion module. The fusion module mainly consists of a 4-layer transformer encoder, which leverages a attention mechanism to gather information from different modalities. The supervision for the multi-modal fusion consists of primary and auxiliary losses. The primary loss denotes the cross-entropy loss on the representation for the whole sequence, aiming to align the fused feature representations with ground truth. The auxiliary loss denotes a cross-entropy loss on the representation of each modality, encouraging the model to maintain individual modality information at the same time. We use top 1 accuracy to evaluate the proposed method. We first conduct experiments on the overall model performance. As shown in the left table, we compare our methods with the state-of-the-art methods on the MMWL dataset in crossview setting. The proposed method demonstrates a significant performance gain on both RGB and RGBD data. We also present the performance comparison with other methods on the crossview sign language recognition challenge in the table on the right. The proposed method achieves the best performance under both RGB and RGBD settings. We further conduct ablation studies on synthetic view augmentation and modality fusion. Table on the left shows the ablation results on background augmentation and viewpoint augmentation. As shown in the table, both types of augmentation contribute to performance improvements, bringing an average performance gain of 30%. Table on the right shows the performance of different combinations of modalities. Notably, skeleton features exhibit great potential under the crossview setting, which achieves an accuracy of 45.99% with the utilization of bidirectional LSTM layers. The combination of skeleton features with either RGB or depth features yields competitive results, while the fusion of all modalities results in a maximum gain of 26%, achieving the best performance, highlighting the effectiveness of the proposed fusion module. In conclusion, we present a synthetic view augmentation pipeline for crossview sign language recognition. Our major contributions are summarized as follows. First, we propose a synthetic view augmentation pipeline to facilitate SLR models learning viewpoint invariant features. Second, we design a multimodal fusion framework to leverage the complementary information among various modalities. Third, we demonstrate the effectiveness of the proposed method in the crossview setting and show its significant potential for real-world applications. Thank you for watching, and please feel free to contact us or access our source code by scanning the QR codes above. We look forward to engaging in further discussions. Finally, we would like to acknowledge the references that supported our work. Okay, so this concludes our presentation. Thank you again for your attention.
Thank you, Yuting's presentation.
Yeah, thank you.
Yeah, and you can stop sharing.
Okay.
Yeah. Let's continue. Let's continue. Thanks to Yuting's talk, and Yuting's team provides a synthetic view augmentation strategy and a multimode fusion framework to enhance cross-view isolated sign language recognition. They reconstruct 3D human mesh from the sign language video, generate synthetic views by transforming viewpoints, and apply background augmentation to improve the robustness. Their XV and SLR model follows a two-stage training process. The first training the single mode models for RGB, depth, and skeleton data. Then integrate the feature use a transformer-based multi-mode fusion model. Additionally, data augmentation and extrusion loss feature enhance generalization. And finally, I will conclude the workshop by summarizing our key findings and discussing future research directions. To summary, the cross-view isolated sign language recognition challenge highlights the difficulty of generalization sign language recognition models across unseen views. Top performance teams apply the view strategies such as synthetic view augmentation, graph-based modeling, diffusion post-generation, and ensemble learning. Will this approach improve the robustness? Significant challenges remain in cross-view generalization, multimodal fusion, and adaptation to real-world conditions. Looking ahead, future research should focus on 4 key areas. Firstly, developing viewpoint invariant features learning using technology like construct learning, self-supervised method, and domain adaptation. Second, enhancing multi-view data augmentation with approach such as diffusion models, advertised training, and 3D post-estimation. And third, improve multi-mode integration by leveraging cross-modal attention, feature alignment, and adaptive fusion technologies. Finally, achieve better real-world adaptation by building more challenge test sets that reflect real environment diversity. By addressing these challenges, future cross-view isolated sign language models will become more robust, generalizable, and developable, helping to improve accessibility for the deaf and hard of hearing community. And this is all of our cross-view isolated sign language recognition challenge workshop. Do we have any question? And yes, if we're not, we will. This is the end of our workshop. And thanks again for the Worldwide Conference and the Coda Lab for test our benchmark. And thanks everyone to attending our workshop. Thank you. Please stop recording.